Ah,
Okay, now it's working.
yes, great.
Cool.
Cool. Then I think we can start. Today we have the pleasure to have the complexity cat himself to be part of it. Is Amahury Diaz, who is who will be a PhD student at Binghamton, and will talk to us about chemical automata. And then the second part was motivation in academia. I completely blacked out. Sorry. Thank you very much. And Amayuri, I think you can start.
Thanks so much. First of all, thanks so much for the invitation too. For me, it's a pleasure to be here and share ideas with you. As I was saying, what I'm going to show you are the results of my master's thesis, which I defended successfully a couple of days ago. So let me start by claiming in a single sentence what I did in this project. I study time series forecasting using coupled chemical oscillators. The rest of this presentation will be dedicated to your understanding of this sentence and how to connect it with network science and complex systems and stuff. So let's start by asking, what is time series forecasting? Time series forecasting is the process of analyzing time series data using statistics to perform predictions based on that data. There are many methods to perform that. Particularly, I'm focusing on error metrics. These measure the accuracy and magnitude of errors in the forecasted values when compared to the actual ones. And from all the many possibilities that are for measure these errors, I'm using the root mean square error because it penalizes large errors to the squaring, and also because it's very easy to interpret. So with that, we already understood what time series forecasting is, but here I'm saying that I will use a dynamical system to perform such time series forecasting. So how can I do that? Let me introduce you to reservoir computing, which is a machine learning framework for time series prediction based on recurrent neural networks. This is the classic architecture of reservoir computing. You have three layers: input, reservoir, and output. In the reservoir, you have this recurrent neural network, and the way it's going from the input.
Mauri, can I interrupt? We don't see your slides. We only see the first slide. So
On the
maybe
first slide. Okay, okay. Oh, okay, okay.
I was unsure if
Sorry.
this was still.
Yeah, okay. Let me then try to. Okay. So, okay, now you see the change,
Yes,
right?
yes, yes.
Okay. So, okay, yeah. So I explained it already. Now you see the changes, right? Okay.
Yes.
The what is time series? These are the error metrics I was mentioning previously. They basically measure the magnitude of errors in the forecasted values with comparison to the actual ones. Particularly, I'm using the root mean square error, which penalizes large errors and it's very easy to interpret. So with that, right now we understood what time series forecasting is. But here I'm saying that I'm using a dynamical system in order to perform this time series forecasting. So how can I do that? How can I use an arbitrary dynamical system to perform time series forecasting? The answer is reservoir computing. This is a machine learning framework for time series prediction based on recurrent neural networks. As I was explaining, this is the architecture of reservoir computing. You have three layers: input, reservoir, and output. This part here, the reservoir, is the recurrent neural network, and the weights going from the input to the reservoir are fixed, while the weights of the reservoir of the recurrent neural network are also fixed. The only stuff that you take care of training in this reservoir computing are the weights going from the reservoir to the output, and you can do that with a linear optimization method that allows you to measure finally the root mean square error. So many people like reservoir computing because it requires small training data sets. So it requires low training cost in general, and this is very attractive for training something. But for me, why this framework is interesting, it's because the reservoir can be very malleable. Like in principle, you should use a recurrent neural network, but nowadays you can find papers of people using in vivo ecological networks as a reservoir. You can use brain organoids as a reservoir, active matter, living beings. So you can put almost anything you want here. And it has been shown that it's possible to perform reservoir computing using any dynamical system if such a system can be represented by a set of differential equations. So with this methodology, we can finally perform time series forecasting using basically any dynamical system. And now we can ask the question, what are chemical oscillators, right? So in 1951, Boris Belousov was looking for an inorganic analog to the Krebs cycle, which is a universal part of metabolism. And this culminated in the discovery of this chemical reaction that you observe here in the pictures. These are different time frames of the chemical reaction. And as you can see, it's changing the color. These color changes represent oscillations in the redox potential of the chemical reaction. And in principle, Boris Belousov couldn't explain why of these oscillations. But years later, Anatol Zhabotinsky discovered the mechanism behind this chemical reaction. And thus, right now, we know this reaction as the Belousov-Zhabotinsky chemical reaction. So with that, you already know already what are chemical oscillators. But here, I'm saying that they are coupled in some way. So again, what do I mean by that? In 2022, it was shown that if you have two couple BC oscillators, they will spontaneously synchronize. This is the experimental set that they use. This is how you can connect, how you can couple two BC reactions. But additionally to this, the authors also propose a system of differential equations representing these two oscillators, such that allows you to reproduce the experimental behavior that they observe. So you can couple both experimentally and also in terms of mathematics. And with this, we're basically done with this sentence. We already know how to use any dynamical system for time series forecasting and also what coupled chemical oscillators are. But of course, now you can ask how. How did you study time series forecasting using coupled chemical oscillators? And well, basically my initial proposal was inspired by this experimental set used in the 2022 paper I show. My idea was, okay, if we can put almost anything here as a reservoir, why don't using a couple chemical oscillators, right? And perform this time series forecasting with them. The problem with this is that doing in vivo experiments can be very expensive in terms of time and money. So before carrying out these experiments in the lab, my idea was to test these ideas in silico, right? So instead of using two real coupled chemical oscillators, I'm using the system of differential equations proposed in the 2022 paper that I mentioned, because the parameters of this system are fine-tuned in order to reproduce the behavior of the real chemical oscillators. So the advantage of also using this model is that they propose equations not only for coupled chemical oscillators, but for uncoupled oscillators and also for single oscillator. So you can use many different configurations of chemical oscillators as a reservoir. So in order to test the capacity of different oscillator configurations for time series forecasting, what I did was to generate a time series with different complexities. So we have this Lorentz system represented by this set of differential equations, and we can integrate it, right? So suppose I integrate the z variable in the interval 10,20, and I will obtain this time series here. So this time series has oscillations, but these oscillations are not so dense, right? I can distinguish each oscillation one from another. But if I increment this right integration limit from 20 to 40, I obtain this another time series. And this new time series has more oscillations. The density of oscillations is higher, and therefore it will be harder to forecast it. Therefore, I will say that this second time series is more complex than the previous one, because the second one is harder than the first one to forecast. And of course, as we increase this right integration limit, we obtain more and more densities of oscillations in the time series that allows you to say that these time series are becoming more complex. So in total, I generated 9 time series to test them in my reservoirs. I integrated from 10 to 20, from 10 to 30, from 10 to 40 until 10 to 100. So there are 9 of these time series. Again, they will use to test my reservoir. And I'm calling these numbers here in red oscillatory levels because they give you information about the degree of complexity in the time series, in the sense of they are harder to forecast. And to test these 9 time series, I'm using 4 reservoirs. These are the same proposed in the 2022 paper. We have a single reservoir, we have 2 uncoupled reservoirs, we have 2 weakly coupled oscillators represented in this diagram by the dashed line, and also 2 strongly coupled oscillators represented in this diagram by the solid line. And the idea is very simple. You will take one of these 9 time series, you will take one of these reservoirs. And remember that each reservoir is represented by a system of differential equations, right? So we need an initial condition. And in the 2022 paper, they propose different experimental initial conditions, which are related to the initial synchronization states between the oscillators. So the idea is I calculated the root mean square error for every initial condition and average those root mean square errors to obtain the average root mean square error, which I call efficiency, for that particular reservoir for that particular time series. So when you perform all the possible combinations, when you have all the possible time series, the 9 time series I mentioned, versus the 4 reservoirs, averaging the root mean square error for every different initial condition that they propose, you can obtain a plot like this. And this plot tells you how the average root mean square error, aka the efficiency, changes with respect to the oscillatory level. So here the labels are very, very straightforward. We have R for ridge regression, and this basically, it's a method which do not use reservoir. It's very common that in the reservoir computing literature, they use this method in order to compare methods with reservoir and methods without reservoir. We have also S, which stands for single oscillator, and U stands for uncouple, CL for couple low, CH for couple high. And these last 3 cases have values of efficiency which are essentially the same to the 6th decimal place. Therefore, all of them are overlapped here in this purple curve. Okay, so before analyzing in detail this plot and what's the meaning of it, remember that as we increase the oscillatory level, we are dealing with a more complex time series in the sense that it's harder to forecast. And the root mean square error is measuring the difference between the predicted and actual values. Therefore, the closest you are to 0, the more efficient you are in predicting, right? So let's pay attention now to this oscillatory level here. This is the 50 oscillatory level. And from this point, 2 interesting things are going on. The first one is that the chemical reservoirs are more efficient than a simple ridge regression. You can observe that by taking a look at the curve of the ridge regression, which is above the curves of the chemical reservoirs. So this difference means that the chemical reservoirs are being more efficient than the ridge regression after this point. And the second thing that we observe is that there is a clear hierarchy of efficiency between the reservoir composed of a single chemical oscillator and the ones composed of 2 chemical oscillators. Why? Because we have this gap here, which I'm marking with the small black arrows. And this gap tells you that all the configurations of 2 oscillators, which is represented by this overlapped purple curve, are below the single oscillator case, which is the orange curve. And this means that in all cases, the configurations of 2 oscillators will be more efficient than the single oscillator. And this behavior is preserved even though you vary the parameters of the reservoir. With this, I'm not claiming that the threshold found will be the same. Here the threshold is 50, and when you change the parameters, could be 40, could be 60, 70, 80, and so on. But you will always find a point such that these 2 behaviors are preserved. And the same happens when you add different types of noise to the reservoir. This means add noise to the systems of differential equations. And again, although the threshold varies, we can always find a point from which the hierarchy illustrated in this plot is fulfilled, in the sense that any configuration of 2 chemical oscillators is more efficient than the configuration of a single oscillator, and the single oscillator is more efficient than the classic ridge regression. So with this, we're basically done. Now you understand in detail this sentence and its whole meaning. I basically show that 2 chemical oscillators will be always better than 1 single chemical oscillator when forecasting complex time series. And now you can ask, okay, but why? Why should I be interested in this research? Why is this relevant in the world of networks, complex systems, and stuff? And to answer this question, let me talk about one of the many problems that we are facing now. And this is that nowadays artificial intelligence is using a significant amount of energy, and this consumption is expected to increase in the coming years. So if we want to keep this relationship we have with technology now, like keep using ChatGPT and Gemini and all that stuff, we should transition it to a more alternative, to a more sustainable computing alternative that allows you to be sustainable with the environment, but also that allows us to keep the computational power that we have now. And if we broadly define computation as any process by which input information is transformed according to predefined rules into output data, then this is the landscape of computations that we have. Here, when we respect the von Neumann architecture, we obtain the classic computation stuff that we know. But when you don't respect this von Neumann architecture, you can have multiple types of computation. And particularly, unconventional computing architectures are outstanding candidates to be sustainable with the environment because they can often operate on orders of magnitude less power than traditional computing systems. And right now we have many proposals for these unconventional structures. But despite this diversity, we still don't know in general how to program them. So what do I mean by programmability? Imagine your favorite programming language. Could be Python, could be Mathematica, could be R, Fortran. In all those cases, you can write a function such that prints out the first 10 positive integers. And how that works is that your computer reads the instructions, goes to the memory and the processor, exchange information, and produce the computation. And nowadays, we don't have a general procedure, a general way to manipulate information in unconventional architectures. Therefore, we cannot make the stuff that we do with traditional computing systems. And of course, this is problematic because if we cannot program something as simple as a function that prints out the first 10 positive integers, then we won't be able to perform this complex stuff that artificial intelligence requires, right? So for a moment, let's focus on chemical computing. This basically consists on using chemical reactions as the substrate of computation. And so far, we have two alternatives for this chemical computing. The first one is a hybrid chemical computing, which means that basically you use a digital interface to perform the programmability of the chemical reactions. This, of course, is programmable. It has been shown very recently, this year, in fact. And on the other hand, we have that there is a non-hybrid chemical computation, which means you will only use the chemical substrate to perform the computation. And so far, we have the major attempt to build a non-hybrid programmable chemical computer. This was done by one of my advisors, by Juan Pérez Mercader. And basically, he showed in 2019 that the Belousov-Jabotinsky chemical reaction is Turing complete, which means that there is an equivalence between this chemical oscillator and a linear bounded automata, which is basically a Turing machine with a finite length. And how this chemical computer works is very, very straightforward. You have as input a sequence of aliquots, which are constant quantities of certain chemical species. They are added to this chemical pot. And in the case of the BC reaction, you should look for a chemical signature that tells you if this was accepted or rejected. Particularly for the chemical reaction, the output is the value of the energy of the free energy difference between the oxidized and reduced states of the catalyst after processing some input. And Juan showed, in fact, that this value is constant, which means that all the accepted words by the chemical Turing machine have this free energy value constant. And given this equivalence between oscillators and automata, in this sentence, I can substitute these two words. So in my thesis, I studied time series forecasting using coupled chemical automata. And since the accepted words by the chemical Turing machine have the same free energy difference after processing some input, we can transform the problem of accept-reject sequences in the Turing machine as a minimization problem, where time series forecasting can be used as a benchmark, and therefore I can replace time series forecasting by computational capability, since computational capability is the process, is the ability of a device or system to process some information. And basically, to summarize, what I did in my thesis was to study the computational capability of coupled chemical automata. Previously, Juan studied the capabilities of only one single automata. So in fact, my thesis is the first study regarding the computational capabilities of two coupled chemical automatas. And of course, now you can ask, okay, what's next, right? And how this is related with network stuff. So first, from the stuff that I show in my thesis, and this spontaneous synchronization that was shown in the 2022 paper, you can show, and I did this in my thesis, that a linear array of n chemical automata will be more efficient always than a linear array of n minus 1 chemical automata. Now, the next step after this is to propose a way to both transfer and control information in these architectures, because we want to manipulate information as we do it in classic chemical computing systems, right? So in my thesis, I put many proposals. One of them is using or building logic gates, like using this spontaneous synchronization to transfer information linearly and build some logic gates with it. The problem with logic gates is that they are very slow. Also, you can try to build Ising machines. These Ising machines were discovered like a decade ago, and you can encode many NP problems as an Ising problem, right? And when you have a machine solving or performing the computations to minimize the energy, you call that an Ising machine. Usually, Ising machines are 2D, but the Ising system is 1D in principle. So also the idea is maybe to encode these NP problems as a 1D array such that you can solve them. That's another alternative for computing. And also another alternative that I mentioned in the thesis is play with this constant value of the energy, right? Because it seems that given the synchronization, you can also manipulate it, like change the value of the energy through time and see how you can perform computations with it. But of course, in general, working with a simple linear array of n chemical automata is very restricted in terms of topology. So what we would like to study is how we can build networks of chemical automata, and if there are any topological conditions that produce higher computational efficiency. So you can think about fully connected graphs, you can think about free scale networks, you can think about symmetric structures that maybe will allow the transfer of information and the control of the same being more efficient in different ways. But of course, there is this problem of how to handle information, right? How are we going to store something in this structure? Is it true that given an arbitrary topology, n chemical automata will be more efficient than n minus one? We still don't know. And of course, this is also an invitation for you to ask, do we have any network science framework which tell us how to manipulate information in complex networks? Because again, when I made the review of the literature, I observed that there are many persons exploring how information can be spread and maybe also how to suppress part of that information, but never how to manipulate, how to store it, in general, how we can grasp any topology or a particular topology in order to store a variable or in order to produce some kind of computation. So with that, basically, I finished my talk. Thanks so much for the help of my two advisors. They encouraged me a lot during the evaluation of this research. And if you have any questions, we can pass them.
Thank you very much. That was incredible. That was really cool. Do we have questions? You can either raise your hand or you can also just unmute yourself and talk if you feel like it. Wait. Do.
So probably my question would be, first of all, thanking the honor, the speaker, because it was very, very nice. And I see a lot of cool stuff from like complex system gathering together, because like we have a lot of things like from like, I don't know, like the machine learning, and then you have the time series forecasting, and then you have a lot of cool things that then you put it all together. My question would be like, how much is the computational power of these kind of things? Because like if it's only like the time series forecasting, can we also use it in order to predict other things? Can we use these kind of frameworks to perform like classification tasks or like annotation tasks or another kind of like things that it's possibly done with other neural networks and the other types of like machine learning?
Cool. Yeah. First, I would like to explain a little bit more this translation from the acceptance rejection problem, basically why I'm using time series forecasting, because of course it's like, okay, I mean, it seems that you start by time series forecasting and then you make a big jump to computational capability in general. So this is related to this plot. Again, as I mentioned previously, Juan, my advisor, showed that all the accepted words by the chemical Turing machine have the same free energy difference. And is this constant value that is shown here. So basically here you are taking a look at different sequences, different lengths, different complexities, as I mentioned previously. And here you have the free energy difference value, and all the accepted words have this 91.6 value. So since this value is constant, you can redefine the y-axis of this plot so that now the accepted words have free energy difference equal to 0, as shown in this second axis here. And thus, we can reduce the acceptance rejection problem to a minimization problem, right? Because now you want to be close to 0 in order to be accepted. And since you have now a minimization problem, like you want to be close to 0, then the time series forecasting could be used as a benchmark to study this phenomena. The interpretation of this is that the more efficient one or more chemical automata are at predicting a complex time series, the more efficient the chemical Turing machine is at processing complex computable languages. Because the only requirement to process a language by a Turing machine is that the language is computable. But it has been shown that if this language is complex, for example, in the grammar, then you will need more resources, like in terms of energy and in terms of time, in order to process it. So the idea of using different time series with different complexity is basically using different complexities of computable languages and see if from one particular computable language you obtain this hierarchy that we observed in the thesis, right? Now, that's only for the interpretation of all this stuff. The second thing is, of course, what Jasmine pointed out, which is, okay, but what would be the advantage of using this with respect, for example, neural networks and all that tools that we have now? Basically, imagine that we have finally built a chemical computer composed of these end chemical connected automata with some topology that allows us to optimize the operation for a sufficiently complex language and all that. So what's next? What are the types of problems for which this chemical computer can be more efficient with respect to conventional stuff? First of all, very, very important to mention, comparing traditional computing systems with unconventional computing systems could be at some point like comparing a fish and a bird. So if you take these two animals and you ask, which is better at swimming, a fish or a bird? Of course, the fish will have advantages. And the problem is that, of course, the majority of the problems that we have now were built or were thought using traditional computing architectures, right? So right now, the traditional computing systems use many combinatorial circuits, and these combinatorial circuits in general are not the most efficient architecture of computation that we have. So chemical computation offers the opportunity to explore models of computation beyond combinatorial chemical circuits. One of them are stateful computations, where basically the output will depend on the current input and also previous states. Another type of computation is a stochastic one. This basically consists on making random choices during the execution of the algorithm. This is related to probabilistic algorithms, which are able to efficiently approximate solutions to difficult optimization problems, which maybe deterministic computations wouldn't able to solve it, right? But maybe for me, the most promising part is to use distributed computations, because this means that you can execute in parallel different parts of an algorithm and then use this substrate, which is the chemistry, to speeding up the computation significantly. So under these different types of computations, we find that chemical computer is very promising. And as I mentioned also previously, there are other alternatives like encoding these NP problems, which cannot be tracked with a classic computer in, for example, arrays of chemical oscillators that, of course, could allow you to also go beyond the chemical or the traditional computing systems, right?
Great,
Oh,
thank you
great.
so much.
Yeah, thank you. Do we have maybe if somebody has a short question? Otherwise, we can also switch to the discussion if you want to.
Yeah, sure.
That would be great. Do you want to introduce the topic and have an introductory remark, maybe?
Yeah, sure. So I'm not sure if it's okay if I stop sharing screen.
Yeah,
Okay.
100%.
Yeah. Well, I will start by telling you an anecdote, which inspired me to talk about this topic. And that's it that in Mexico, when I was an undergrad, we all as undergrads should have something called social service, which basically it's a research stance of 6 months or 1 year with another person in order to gain some experience, maybe in research or industry, depends on the social service that you took. And in my particular case, I decided to do the social service with a person who was working at that moment in the origin of life. And this person even gave me a scholarship, so we are doing very, very well. But this person, just to contextualize, this happened at, like in 2020, a little bit before the pandemic stuff. So the pandemic starts. Basically, we started to meet, but I still had the scholarship. We still could meet by Zoom and all that. But currently, this person passed away. Like basically, the person I was working with passed away. I was not having a very good moment at that time, and of course, my worries after he passed away was okay. What should I do with this social service because it's a stock and what's going on there, right? And what the institute at that moment offered me is to keep my scholarship, but I should switch the project, right? I should not work with the same person because this person, of course, passed away, but I should select another person or they assign it to me, another person in order to work with. And that's how I ended doing material science as my social service. Uh, Nothing personal against material science, but being honest, I passed from studying the origin of life to materials, and of course, for me, it was more exciting to learn about the origin of life with respect to the material science. And from that experience, I learned that for me, it's very, very, very important to feel passion of what I'm doing in order to do it okay, right? Because for that whole year, it was a very long year. I learned a lot of material science. I learned a lot about crystals and organic compounds. I learned how to access to remote services, remote servers, and all that. But the problem is that, being honest, I never felt passion about it, and at some point, I felt frustration of what I was doing because it was not something that I felt attraction or passion to. So the first question that I would like to ask you is, do you feel passion for the stuff that you are doing now? I mean, maybe some projects are super exciting, like, yeah, I will solve this question that maybe many people has been trying to track, but maybe other projects are more like, I'm doing this because my advisor put me in the grant and I should work on this because of the grant. So have you felt any feeling recently?
I can start, or and then other people can already think about it and then can chime in. Uh, I think that's first of all, a very cool, not a cool story, but like a very interesting story, and your experience in that is very, very interesting. I think everybody struggles from motivation and passion as an up and down process, and sometimes you cannot predict where it is right now. So at some point, for me, I decided it's better to not be passionate, like not don't look for passion within each aspect of a project, but more with long-term goals of understanding and improving. So for me, self-improving in the sense of figuring out that my skills improve or my understanding improves is a bigger motivator than solving, I don't know, solving a ranking problem or solving a simulation problem or whatever. Yeah, but it's very tough, especially if you cannot choose, if you don't have as much choice in your project, right? A lot of people, young early career researchers, are maybe hired for a project or they have an overarching project, and then you have to accommodate other people or you have to accommodate the big picture in your thesis. So you have to be creative to figure out other ways of motivating yourself.
Yeah, I kind of agree. I was lucky enough to like end up in the right place at the right time, let's say. So I kind of chose my PhD project and then I basically remain the same area. And yeah, I think that it's some kind of trade-off between finding someone that you're passionate about and like time that goes by, because it's not like it's yeah, and my comments are always a little bit sad but realistic, because we don't have like infinite time. Like for me, research is more like leverage time to get the most of it, let's say. And so we don't always have like the time to find something that you're passionate about. So there's always like a big portion of luck in finding what you have to work on. But I think that's in some maybe even like a small part, you have to like it, to like what you're doing. Otherwise, it would be a little bit of a nightmare, I think, working always on a stuff that you hate. And I hope that no one of you like are studying something that they hate. But yeah, that's my 2 cents.
I can also a bit continue, but maybe from another point of view. Because, for example, I wanted to study like in my bachelor's, like computer engineering, and I was accepted into computer science. And in my country, there are two different things. Like one is really software developing, and another one is like really research based. And I wanted to do something with computers because I saw like a path that I can find myself working on it. But computer science was quite tough for the first 6 months. It was like so bad. But I don't know like what really happened, but I felt like the love and also passion into it, and I changed a lot. And I tried to like find the best thing that I could do like in my bachelor's, and then I was introduced to network science. But right now I feel like it's quite different problem. I'm interested to everything. Like for example, like I cannot really choose between different things in network science. If you give me a project about like I don't know like what you're talking about, I'm interested. If you give me something about like computational social science, I'm still interested. So these kind of things for me it's like a time manner, meaning that if I put a lot of myself into myself, I mean like a time and energy into something, I would like it in the end, because it's not like me hating it, because probably sometimes we have some kind of like thing that we can change, but sometimes we cannot change. And if you accept that you cannot change, it's probably better to like it, to not suffer. So this is like my point of view. So like maybe if we just accept that if nothing is changeable and you're happy with what it is, but you're not comfortable, maybe you can try to work on it. But if you are not comfortable and you are not happy, probably there is some room to change.
Yes.
And even you don't like maybe quitting the PhD and starting over, it's also nice. Doing like quitting your master's is also nice. Like it really depends on like if you're comfortable and happy. Like this is like a different thing.
Yeah, I think that the general way that science works nowadays for young researchers is that you're accepted to some a program, and you basically join a research group which has already research lines, and in those research lines there are problems, and you're assigned one problem, right? So if you are lucky enough, then you end doing exactly what you like it, because maybe you had previous experience on it and you are very interested in that topic. If not, of course, you end struggling working on something that you don't like. And again, I have the opportunity to talk about this stuff with many young people during the summer, young researchers as us. And I detected a constant behavior in the advisors, and that's that the advisors usually are focused on doing their own research, and they basically barely care about the research or the problems that maybe you are interested in solving. Uh, in my case, that's not holding, because for example, my advisor allows me to work in whatever I want, in the sense that, okay, I mean, if you know a problem I can guide you towards that problem. I can contact you with some people working in those problems, and based on that, you can work on your own ideas. But in general, you are working for the ideas of someone else, right? For the ideas of your advisor, and of course, that couldn't be encouraged enough. During the summer, I visited Italy, and I had the opportunity to talk with Luca Allegri, which is one of the students of Manlio da Domenico. And he told me something that really astonished me, which is that Manlio sometimes allows him to not only work on his the project, like, let's call it like Manlio's project, but also on his own ideas. And for me, maybe one first solution to this problem of motivation in academia is that the advisors should be, well, not obligated, but should have this ability to let you work on your own ideas, and also at the same time work maybe on the ideas of the advisor, because of course if the advisor is funding you, and the grant that you got basically is helping you to keep your studies and all that, you should contribute in some way to the work, and how to say, accomplish that part. But also maybe that if advisors start to let students work on their own ideas, then you can also have interesting dynamics going on.
I have a comment to that, which is something that I feel is true. Maybe other people feel different, which is that especially for a PhD student, more important than finding like applying to a program where you like the topic or where you feel like it's the best match with the topic, you should find a supervisor that is aligned with how you see the world, research, like the world of academia, and where you think like you can learn the most, and then that connects to what you said. If you find somebody that allows you a healthy balance between research that has a chance to it has a chance to be fruitful in the sense that you can get some results and do some work that you can publish, but then also allows you to explore a little bit on the sides. I think that's very, very important. And every time, more for me personally, every time I come in contact with more senior researchers that don't allow for this wiggle room, or like say, oh, this is how I want to do things, and I look for PhD students who do that, and then I don't know, we publish great papers or whatever. I think for me it's always a red flag, because I know that if I don't like it, then chances are you at some point you won't like it, even if you like the idea of a project. At some point might come the point where you don't like it, and where you need some flexibility, I think.
I think what you said is quite important, because flexibility is like the part. Like if you are also told like from the first year of your PhD or end of your master's, like somebody tells you, yeah, I mean, you are able to do whatever you want, it is also probably lowering your interest in that topic. For example, you are a master's student and you wanted to do network science. The professor said like, this is the book, and this is the, like, for example, you should do something in higher order networks. If you don't know what to do, like what should be the research question, what could be like the path to do it, it would be also very difficult for majority of people to do so. So I would like to say this balance is quite important. Like sometimes like you do your own things, and sometimes you do like the things that the professor says. And one great initiative, like the winter workshop of the complex system, for example, is that you can bring new ideas to other people and work on it, for example, and something like aside your PhD. But that's also important, because like you have to do like something that you're passionate about, rather than like doing things that you should do. So I think the balance is more important than like doing all the time things that you are passionate about.
Yeah, I would also like following what Yas just said. I think one aspect that was really important for me during the PhD to keep motivation was attending summer schools conferences and so on. After each event, I usually come back really motivated, and it lasts for a couple of months at least. That strong motivation, just like on science, let's say, just because I discuss it with people and so on. Then of course, uh, yeah, you need to like keep motivating it with the project and so on. And I agree with what all of you just said, but I think it's also important to discuss with people, go to conferences, that sometimes also other people can remember you, why you are motivating, and why you like stuff, and you know uh, how to keep going with the project, even if you don't like it, but maybe you are almost done, and so just to keep the last sprint to finish the project, let's say. So I think like events, social events, are really important in keeping motivation.
Also, other way around is also possible. You go somewhere and you understand like what you were interested about is like not something interesting. So it's like also
Yeah.
possible. Like you go and present your work, you don't give people don't give you like good feedbacks, and then come back like not motivated enough to do and continue your project. So maybe that is also nice.
Yeah. Also, because sometimes also, sometimes quitting is also a choice, and can be also the smartest choice in some situation. And it's very useful to learn that and, act in that sense.
Yeah, I mean, definitely, I think that we all agree that the balance between working on your ideas and working on ideas of your advisor, it's necessary. Sometimes that's not the rule, at least with the people I have the opportunity to conversate. Usually they are working on the ideas of someone else, and of course that could be disencouraged. Uh, but also I think that in general, science right now it's like having a crisis of how to say it. Uh, in general, why the advisors want to work on some ideas is because maybe if they work on those ideas, it's I don't know, it's likely that they get certain grants, right? So for me, that means that right now science is being guided by the money, and of course that causes that many people from very prestigious universities, like here in the States, for example, from Stanford or Harvard or whatever, can even fake results in order to publish something interesting in papers of like Nature and Science and so on, and then get the grant like that they were looking for, right? So I think that also that's a problem that could be like behind this sometimes toxic dynamic that advisors have with their students. Like, you should work on this because I should work on this because this is what it's giving us money. And of course, it's very hard to try to change the scientific publishing paradigm that maybe we have now. But there are alternatives that currently, even in the complete system society, we are trying to develop and to promote, like try to create journals that do not follow these metrics of publishing a lot to have this recognition or to get a grant. So from that perspective, yeah, what do you think? Is the scientific publishing paradigm nowadays uh, to be changed, or do you think that really affects the way that you do science now?
I think it's on the brink of changing very rapidly. Uh, as soon as the editors cannot handle ChatGPT written articles, like the amount of articles anymore, which is pretty soon, I think, then something will change. Also, it already changed in how faculty is hired in some places. That not the number of publications determines if somebody's hired or not, but more the in-between thing, or also the quality of the stuff and how the thematic fit and the personal fit is. So I'm hopeful that this like long-term trend of trying to publish as fast as much as possible, even if it should have been maybe taken half a year longer, more thoroughly cross-checked with try to break whatever you can break with your stuff, and then see if it still holds. Yeah. So I'm hopeful, I guess.
Yeah, I mean, what you were saying, I think connecting it with what was the idea of like this discussion is that like they are doing it to get more grants, and they are not doing it because like no, not like they are not doing it, but like they are possibly doing it for the grants and not because they are passionate about. And that's like sometimes that it's also like a balance for them. Like maybe they have to like do these projects by their own time and not on the time that they are like they have to do on a like a funded project. And this is like something that you should do research that you are not passionate about. You have to make it like grant worthy. You have to make an impact. You have to do like a lot of things. So yeah, I think the fact that we need money to do research is like something that affects this probably like the motivation and everything. So if money was excluded and like every researcher was like getting like a constant money till end of their like I don't know like the career, maybe they try to do like things that they really like. And probably this is also happening. It's still like in many countries, I guess some professors they don't need to do grants and they are provided. I think Gabriela, is that true that in France it is like this for some people, that if they are good researchers, they're provided money till end of their career?
I don't know about that, honestly.
Okay. So, this is, but I know, like for example, like the CNRS, like people, researchers, if they are good enough, they are selected and they are provided money till the end of their career. So they're basically focusing on whatever is interesting for them, and that's also something nice. And if the money is putting it aside, probably this problem can be also fixed. So
Yeah, I mean, something I have learned from senior researchers is that, I mean, of course, money is important because that's how you live or the stuff that you need to live. But some of them work, or I mean, if they diversify their projects, then one part of their projects could be dedicated to the grant stuff. You know, like okay, we will solve a social problem or economical problem or ecological problem, whatever, to get the money. But another part of the projects are more dedicated or more focused on how to say more non-application or maybe at least not so direct application science, you know, like this interesting stuff. For example, of the origin of life, I was mentioning at the beginning, right? So maybe that also can be taken as another strategy for the advisors, not only focusing on the grant, but using the grant as a source of getting money, but diversifies their projects so their students also have something more interesting to do, and also not only pursuing the goals of someone else, because of course if they are give you money because of that, because could be relevant, right? So I think we're almost to about reaching the hour. So would you like to wrap in some way or yeah, I'm
Yeah,
not sure
I
how.
yeah,
Yes.
I first of all, thank you all for the discussion. I think one of the nicest things that have been said are the things that I think it was Francesco who said that like the community uh, keeps him being motivated even either in conferences like in online offline events, but also online for me. Also these seeing online people that I care about is very nice. Um, yeah. Do you have any last words for this? Then thank you very much. And I think uh, I wish you a great Thanksgiving for everybody who celebrates or eats and great feast.
uh, Thanks so much again for the invitation, and
Thanks,
yeah,
Yuri. It's very nice.
Bye.
Bye bye. Have a
Thank
good
you.
day.
Thank you. Bye.
Bye, Mauri.
see you.